model. So I assume that Dr. Xuan Xie, you will be the presenter, am I right?
Yes, I will be the presenter.
Okay, thank you. So for the second paper, fast push-down reachability analysis with application in network verification, may I know who will be the presenter? And the author of the second paper here. Okay, so how about the third paper? The third paper is live synthesized. May I know who will be the presenter? Okay, so I think it's the time now. We can start this session. For this session, we have 3 papers. It's about the verification technique for neural network model and the online runtime system. Now let's invite the author or the speaker of the first paper, the property directed verification and the robustness certification of recurrent neural networks. So let's invite Dr. Xuan Xie. Welcome.
So should I share the screen?
Sure, please.
Can you see my slides now?
Yes.
Okay, then I just start. Okay, hello, everyone. I'm Xuan Xie. Today I will give a talk about a novel abstraction-based approach to verify recurrent neural network. This is joint work with Daniel Rajashi from Max Planck Institute for Software Systems and some other collaborators in Paris and the University of Lübeck. And let's get started. Neural network is everywhere. We have seen a lot of impressive application of neural network, from stuff like robot control, speech recognition, machine translation, and autonomous driving. Neural network plays an important role in them. So neural network seems to be taking over part of our daily life. However, neural networks are error-prone. Recently, people have discovered that neural network, which is sort of like a new type of program, can be buggy as well. What you are seeing on the screen is a well-known experiment, which is done a few years back. Essentially, some researchers show that adding some small perturbation on the original picture, the neural network, which is responsible for recognizing the image, will basically misclassify this pic as airliner. And this is problematic. And in the formal verification community, many verification approaches have been proposed to address the verification problem for feed-forward neural network. There are many studies focused on adversarial examples on network operating on image tasks. However, in natural language processing domain, where recurrent neural networks also play a huge role, adversarial example is still a type of serious bug. So let me take sentiment analysis as an example. It basically takes some sentence as input and output the sentiment of the sentence. For instance, if we input "this is a beautiful product" to the network, it will tell us it is a positive sentence. However, if we switch A and U in beautiful, which is like a small perturbation, the network will say this is a negative sentence. And this is, of course, problematic as well. Different from the work on feed-forward neural network, fieldwork work is on INN. So let me introduce a recurrent neural network with more details. A recurrent neural network, INN for short, is a class of artificial neural network where connection between nodes form a dialectic graph along a temporal sequence. INNs can use the internal state to process variable length sequences of inputs. And it is central to natural language processing tasks like sentiment analysis, speech recognition, and machine translation. So in this work, we focus on verifying recurrent neural network. In other words, show that the INN satisfies some desired property. For example, autosol robustness is an important type of property. And it basically requires that no inputs in the neighborhood of the given input has a different prediction. So this field is quite new, and there are some existing work, but they mainly have two limitations. Some work perform verification by means of the internal structure, internal information of the network, and they assume all the information of the network model is accessible. For instance, a recent work unrolls the loop structure and reduces the complex problem of verifying recurrent neural network into non-recurrent problem. However, this approach will not work in black box context. In real world, many neural networks are not accessible, like those used in companies. In this case, black box verification is required. Another line of work leverages the stateful nature of INN to extract an abstract model from the network. For example, Markov chains and finite state automata to perform analysis. Nevertheless, they didn't conduct refinement to the abstract model, which means that their model is not precise enough for analysis. To address the aforementioned limitations, in this work, we propose probability-directed verification of recurrent neural network. The two key advantages of our work are that it is suitable in black box context, and we leverage probability-directed refinement to refine our abstract model. So how do we do this? Let's change our machine learning view to formal verification view and record some knowledge about automata theory. In this verification problem, we are given an INN and the desired property. For the INN, assume it is for classification work. It can be considered as a function that map any input U to a fixed set of classes. So in this case, we can consider the INN as a language, which is a set of in sigma star. Moreover, for the desired property, we also consider it as a language. For example, in the case of autosol robustness, the neighborhood is essentially a set of words that contains all words that can be considered as after small perturbation to the original word, which is a language. And the overview of our work is like the following. We are given an INN and a desired property we would like to verify. At first, we perform black box learning to learn a finite state automaton A as a surrogate model to represent the INN. At the same time, we represent the property as a regular language D, that is, another finite state automaton. Then, we use a classical automata theoretic technique, conducting an inclusion check to check whether all the input accepted by the surrogate model is also accepted by D. It will either return yes or no with the context sample. So Let us consider the case of yes at first. Notice that the surrogate model we learn might be imprecise because of the complicated internal structure of INN. Therefore, we perform statistical model checking to check whether there's inconsistency between the network and the surrogate model. If there is context sample, we put the context sample back to refine the model. Otherwise, we return the result, claim that the property is satisfied. And let us consider the case of no with context sample. Notice that the surrogate model can be imprecise, which means that the context sample W can be a false alarm. Therefore, we use the INN to check whether indeed W have a different prediction. If it is a false positive, we feed it back to our black box learning algorithm to refine the surrogate model. Otherwise, we return the result, claim that a context sample is found. Then let's look at the black box learning part and converting the property into regular language part with more details. At first, let's look at the part of representing property in regular language. The main advantage of representing the property as regular language is that we are able to do a classical model checking computation, the inclusion check of the surrogate model and the property. Many property can be represented as a regular language. For instance, autosoro robustness. Recall that autosoro robustness means that no samples in the neighborhood of the given input has a different prediction. And it requires a concept of neighborhood. Typically, the autosoro robustness verification approach only support one kind of neighborhood. However, in our approach, we can flexibly model various kinds of neighborhood, like Hamming neighborhood or Lewinstein neighborhood. And this neighborhood can all be modeled into the regular language and then be symbolically checked by our approach. Let's then look at how we perform black box learning to extract the surrogate model. For our black box system learning, we leverage an active automata learning algorithm, LSTAR, which is a learning procedure involving a teacher and a learner. The teacher in our setting is the neural network, and the learner's goal is to learn a finite state automaton. The goal of LSTAR is that the learner learns a target regular language from the teacher and outputs a unique minimum automata A, such that A is equal to L. The teacher has access to the target language, L, and can answer two kinds of queries from the learner: membership queries and occurrence query. For membership query, the learner provides a word W to the teacher, and the teacher returns yes or no, depending on whether W is in L or not. For occurrence query, the learner provides a hypothesis automaton to the teacher, and the teacher returns yes if L is equal to A, or a context sample with context sample U with U is in the symmetric difference of L and A. Notice that in practice, occurrence query is hard to achieve, and here we use statistical model checking to get a statistical guarantee that two models is close enough. After introducing two key parts of our approach, black box learning and representing property in regular language, let's look at the experiment part. For the theoretical result, we also have a main theorem in our paper, and I describe it in a high-level way here. Suppose the aforementioned algorithm terminates using statistical model checking for inclusion check. If it outputs context sample W, then W is a context sample. Otherwise, the INN satisfies the probability with high probability, and the probability of finding a context sample is very low. The proof idea is basically two-part. If a context sample is returned, it has been checked by using the surrogate model and the INN. So it is indeed a real context sample. On the other hand, if no context sample is found, based on the guarantee of statistical model checking, we can claim that the INN satisfies property. And the interesting reader can refer our paper for more details. And in the experiment part, we have asked several research questions. And here, I focus on two key research questions. The first one is that how efficient is our probability-directed verification approach on verifying adversarial robustness, as it is the most popular properties that people care about nowadays? The second research question is that how efficient is our approach on verifying the correctness of the INN used on contact tracing, which is a real-world use case in this pandemic period. Let's look at the first research question on verifying adversarial robustness of INN at first. We compare with statistical model checking, which is essentially a form of random testing to check whether the sample is upsetted by the INN is also upsetted by the probability. We ran the experiment both on symptomatic dataset, like a modulo 2 regular language, and real-world benchmark like e-commerce. This dataset can all be transformed to automata, and we can perform check verification on top of it. And in total, we select 200 samples in these datasets to evaluate our algorithm. And the probability we try to verify is adversarial robustness. And this figure represents the result of the efficiency comparison. And the x-axis and y-axis both represent time in seconds. The x-axis is our approach, and the y-axis is statistical model checking. Each cross in the figure represents the verification procedure of the same sample using both approaches. We can see that in most cases, our approach is more efficient than SMC, except for the case that when the size of the sample is small, length is less than 30, SMC is faster, because in this case, SMC can explore the whole neighborhood efficiently. So the take-home point here is that our approach is efficient and effective. The second research question we ask is the efficiency of our approach on verifying INN's correctness that are used on contact tracing. The INN we use here is supposed to learn the trace pattern and identify whether a given trace is contacted with suspicious cases. And I'm sorry. We also compare with statistical model checking, which essentially is a form of random testing. And we run the experiment on social pattern website, which contain information about interaction of human in public places, like hospital and school, presenting as graph. And for property, we use DFA that accepted all possible paths in the graph, which allow us to check the INN, whether the INN learned unwanted traces. And these two figures represent the result of our experiment. And the figure on the left is the execution time of our approach and SMC. And the y-axis is the average time in seconds. The green bar represents our approach, and the blue bar represents the statistical model checking. We can see that in this case, our approach in general is not so faster than SMC. However, let's look at the figure on the right. The figure on the right is the length of contact samples that found by both approaches. The x-axis is the length of the contact sample. Our approach also found smaller contact samples in this case. Smaller contact sample help in identifying the underlying error in the RNN, while long and random contact sample provide much less insight. For instance, from the contact sample returned by our approach, we learned that the RNN overlook certain edges in the trace and identify wrong edges in the traces. And the take-home point here is that our approach is efficient and can find smaller contact samples. To summarize, in this work, we introduce property-directed verification of RNNs. Our approach leverages black box learning and use property to guide us to perform refinement. Moreover, we represent properties in the form of regular languages, which enable us to perform classical model checking approach. And in the experiment, we show that we are more efficient than the classical verification approaches. That's all. Thank you.
Thanks, Dr. Xuan Xie's presentation for this work. It is really interesting topic. For the audience, do you have any questions for Dr. Xuan Xie? Don't be shy. Feel free to ask anything. Okay, so if there's no questions, I may have 3 to 4 small questions or comments for you. So overall, that is very interesting topics to convert or transform RNN into automata and perform the verification. So based on your experiment, do you have any evaluation on how close these two models are? So given a model RNN, given a model automata, and is there any evaluation of how close these two models are and how close their performance? Is there any result here?
Yes. Let me maybe show slides. Oops, I'm sorry. Yes. In our paper, we have shown and proof that because we use statistical model checking to check how close is the surrogate model and the RNN, and we can get a statistical guarantee that to find a contact sample that it is not.
Yeah, I see. So you have some theoretical guarantee. So
Yes.
as there's maybe it is lack of time, lack of space here. So maybe I can ask a little more details. So when you are transformed RNN into the automata, how do you select the variable to represent the state?
I'm sorry. How do
you select the variable, or how do you select the state? The state variable. How do you select it? Is there any? So anyway, so some state of the inside RNN have to transform into a state automata.
Yes.
Right? And how do you make such a? What is the rationale to make such a conversion? And basically, if from intuitive point of view, we may select some state variables to convert to some variable to represent one state in automata, right? So how do you make such a selection? Can you be more specific on this part?
Yes. So for our automata learning algorithm, we use L star. which is basically based on 2 queries. And depending on how we're selecting the state, actually the state can be different based on the learning algorithm. Yeah, because there may be several kinds of automata that can be used to represent the INN. So the state is like provided by the learning algorithm here. But we can, because it is like a flexible framework, we can also represent this L star to another algorithm, another automata learning algorithm, to achieve the goal of like learning the surrogate model. But to your question, I think the answer is that the state here, it is like provided by the L star.
Yes. Discovered by L star algorithm.
Yes, yes.
Are you checking into the internal state of R? For example, when you give an input, you look into the internal transitions and the value of activation function to infer these kind of information.
I'm sorry?
You can think about it. So when we have a sequence, right? We have a sequence. So when the input data is input into the models, it will generate a lot of internal activation function, generate a lot of internal activations inside the network. So have you ever considered this information to construct your automata?
Yes, I think this is a very good point. Yes, but in this case, we just use the black box learning algorithm. But I think what you said, it required white box information of the network to the network. Yes, but our goal is like to perform a black box learning algorithm here.
Okay, so my final question is that it seems that your property is defined on a miniature 1R model. Miniature 1R model. That means given a sequence and you generate true or false, or given a classification. So,
Yes.
but for there also miniature many R model. That means given a Chinese, you interpret it into English. So how generalized? How do you think your approach can generalize to the miniature many models?
You mean that the property we are verifying?
I mean the model you're looking to seems to be a miniature 1R model. A miniature 1R model means that the input is a sequence.
Yes. And
the model will output a prediction, true or false, or which class it falls into. And for another type of R model is called a miniature many R. That means the input is a sequence of language like English. You like to translate into the Germans or French. Okay, so for the miniature many R model, do you think your approach can be very generalized, or is that can be generalized to this part of the model, or how much modification or improvement will be conducted on your current approach to achieve this, to apply on this kind of miniature many R model?
Yes, this is a very good question. In these papers, we mainly focus on like the INN that give yes or no to the input sentence. And in this case, it can be easily transformed like to the automata, because automata can accept it or just reject it, the input cases. From the case you mentioned, like given a sentence, give another translation sentence of the and by using the INN, I think in theory we can achieve this by like one versus all technique in machine learning. Like we use multiple automata to learn the INN and to represent the output of the INN in multiple way. But in theoretical perspective, I think is achievable. Yes.
Okay. Thanks, Dr. Shenxie's presentation and answering for the questions. So maybe it's time for us to move to the second papers. So the second paper is faster push-down reachability analysis with applications in network verification. So the presenter will be Dr. Morten Konga Show. Okay, Morten, please.
Yeah, thank you. Just a minute. All right. So do you see my slides in full screen?
Yes, you can see the clearly.
All right, thank you very much. Yeah, okay. So my name is Morten Skov. I'm a PhD student at Aalborg University in Denmark. And our paper is called Faster Pushdown Reachability Analysis with Applications in Network Verification. So let's try to break down this title a little bit. So a pushdown system is a well-studied formal model. It consists of a finite automata and an unbounded stack. The transitions in the automata have rules, and the top label on the stack determines which rules are enabled. Each of these rules can either push, swap, or pop labels in the stack. So if we take a look at a simple example, here in this configuration, we are in the state P1 and the stack has Y on top of X. So now we can apply rules to change the content of the stack or the state that we're in. So this is an example of a small trace through a pushdown system. Next, let's take a look at a type of computer networks called MPLS networks. These are widely used within the infrastructure, like the backbone infrastructure of network providers. And for our point of view, they have each router has a pre-installed forwarding table where the forwarding is based on labels rather than IP addresses, which is common in other types of networks. Each data packet has a header where there is a stack of labels. In this example, it's just has one label. And the forwarding table determines the operation. For example, here we swap a label, and it also forwards it onto the next router. So clearly there's some similarity between these two, and we'll argue that we can use pushdown systems to verify properties about these MPLS networks. Now, why do we want to do this? So these networks are often manually configured, and this tends to be error prone. And you regularly hear about these that a human error was the root cause of some network outage. And the reason it can be hard is that link failures can send packets onto a backup route, and then if you have multiple link failures, it can be hard to reason about how does this network behave. At the same time, there's a high demand for reliability, security, and performance. So this suggests that it would be good to do some sort of automated verification. Furthermore, the changes to this network, there's frequently changes to the network and to the configuration. So that means that when we do verification, we need it to be fast. And that's the motivation for this paper. That's the topic here. So using pushdowns to verify network properties in these MPLS networks is not a new thing. The first tool that did this was called PREX a few years ago. And later the tool Allwines improved. It came with some other improvements, but also it has a better implementation that speeds up by about an order of magnitude. And to speed up the verification even further and hence scale to larger networks, we needed to develop some new techniques. And that's what we do in this paper, and it gives another order of magnitude. So we present here 3 techniques for faster pushdown reachability. And these are general techniques, but we apply them to make MPLS network verification more scalable. So the first technique is an early termination technique where we construct the product of 2 automata on the fly. Secondly, we to combine two existing algorithms into a bidirectional search. This has a surprisingly high efficiency in terms of improving performance. And finally, we apply this technique of counterexample guided abstraction refinement. So first, a few more details on MPLS networks. As we saw before, a packet that arrives to the router will normally take this path, for example, where we swap to another label and forward it through this path. However, if there's a failure on this link from A to C, the router A will locally detect this, and it will immediately switch to the second priority, like this backup path, where it performs now two operations, both swaps and pushes, and the packet is routed through this backup path. So this is a technique they use to provide resilience in these networks. And we need to be able to model this when we want to verify things. Also note that we have a sequence of operations at each router. Yeah, so in prior work, we've seen the query language, and we use this to specify the types of traces that we're looking for in an MPLS network. And we can either, depending on the type of property we want to verify, we might either want this trace to be there, or we want to make sure that there are no traces that satisfy this. The query language consists of three regular expressions. First, we specify the initial headers that a packet can start with this kind of trace, then the path of links that it traverses, and finally the final header. And then this number K specifies the maximum number of failed links that we consider. And we ask, does there exist such a set of failed links where a trace satisfies these regular expressions? So the way we model this, also the way we convert this into something we can verify, is that we first transform the regular expressions into finite automata. And then we take this path finite automata and couple it with the network. As we saw before, the networks are quite similar to pushdown systems. I'll get into detail in a bit later. So this gives us a pushdown system. And then we use the NFA for the initial stack together with the beginning of the path to define the set of configurations in the pushdown that we call initial. And similarly, we make the set of final configurations. And then the question for the model checker that we develop is does there exist some initial and final configurations such that there is reachability through the pushdown system. One quick note on failures. So this is covered by prior work, but we need to do an over approximation on the behavior when we do failures or when failures happen. And then we need a trace from the pushdown, and we validate that this trace is actually valid from the networking perspective. But in our experiments, it's almost always valid. So we don't worry too much about that now. So let's take a look at a small example. So this here is we call it a topology. So that's the graph of the network with the routers and the links. And this is a small routing table. And then we have a query. This query asks whether there's a trace that starts with 10 on top of some stack of labels in the header. Then the packet traverses, starts on E0 here and exits on E5 with some number of links in between. And the final packet should have only the label 30. So it generates this pushdown. And I'll leave most of the details for you to read in the paper, but I'll just highlight a few things here. So what we see here is that this entry in router V0, where if the packet arrives with label 10, then the router swaps to label 12, is converted directly into a pushdown operation. If we have a sequence of operations, we need to add some intermediate auxiliary states in order to do both operations. And the way we use this path expression is when we convert it to a finite automata, we use the states of this automata S0 and S1 in our push down. So that way we make sure that any path through this push down matches a path through this automata, and then the path expression will be satisfied. Yeah, so this is also defines the initial state and the final state of the push down. So now to give a little bit of notation, the push down consists of states P and labels gamma, and then we have some rules delta. And a configuration, as we saw before, is a state and a word, that's a stack of labels. And the semantics, when we talk about reachability, is in this infinite transition system of configurations, where the each rule in pushdown generates these transitions in this transition system. So if we have a pop rule from P1 to P2, then for any word that starts with X, we can transition to P2 with a word that doesn't have the X on top, and so on for the other rules. Now, in order to talk about reachability and to analyze this, it's very useful to define the predecessors and successors of a set of configurations. And it is defined in the expected way based on this transition relation. So of course, when you have an infinite transition system, we need a trick to be able to analyze it. And this is also like well-known stuff from literature, that we need to represent a set of configurations using a finite automata. So if we look at an example here of a pushdown system, then we define, we can have an example of a P automata here, which defines this set of configurations. So the state P2 with YX on the stack, and the state P3 with XX on the stack, corresponding to these two accepting paths in the P automata. And we call a configuration or set of configurations regular if it is accepted by some finite automata. And this is useful because these pre-star and post-star, so the successors and the predecessors, preserve this regularity. This is an old result by Bishop. Yeah, so, and we also have a saturation procedure that can compute pre-star and post-star in polynomial time and efficient algorithms for this. Also relatively old stuff. So how do we do better than this? And that's the techniques I'll discuss here. And this algorithms work essentially by adding transitions to the P automata using a few simple rules until it saturates these rules. So a small example, the same pushdown system, the same P automata. Now the pre-star algorithm, without going into detail of how it does this, it adds these transitions to the automata, and now this automata accepts exactly the predecessor configurations of this original set. So now we're ready to define the problem of pushdown reachability. So given a pushdown system P and an initial and final P automata A and A prime, we want to see if there's some initial and final configuration such that there's reachability in the pushdown system. And the two ways to do this is to either find pre-star of A prime and see if that intersects with A, or vice versa, to do post-star of A and see if that intersects with A prime. And this intersection is also textbook product construction of automata. So the first technique, as I said, was early termination. And in order to do this, we need to construct this product automata on the fly. So now in the top, we have the original A, and we are building the pre-star of this automata. And then we have some A prime here that we are intersecting with. And already before we begin the saturation procedure, we can start by adding a few transitions. So the product automata, here we have the states are pairs of states from the two input automata. And we can see that in P2, both of these automata can take a Y, which gives this transition, and so on. So now when we add a transition using this saturation procedure, this gives rise to some new transitions in the product. So now P2 can also do an X in this green transition, and we can do an X down here. So this gives us this transition. And now the algorithm continues from this state. We can see that the green state 3 can do an X, and we can still do an X. So we continue here. And once again, now we can do an Y in both of these automata. And already now we arrived to a final state in the product automata. And that means that we have a proof that the intersection is not empty, and we can already early terminate now. So to show you what computations we don't have to do when we do this early termination, let's try to continue adding rules to a pre-star using the saturation procedure and showing what happens to the product automata. So you can see, of course, this is a small example, but we saved a lot of work by terminating early using this on-the-fly technique. So the idea to why this works is that the language here is monotonically increasing when we add transitions to A. Yeah, and we construct this on the fly by only having states that are reachable from the initial state. And then when we add a final state, we know there's a path. So that's the nice construction we have. Yeah, for more details, see the paper. The second improvement that we present is to combine these two existing algorithms called pre-star and post-star into a bidirectional search that we call dual star. So we already saw before the first 3 of these bullet points that you can find termination based on pre-star or post-star, and now we show that you can also do post-star on the original and pre-star on the final, and find where they meet. Of course, this only saves computation if we do early termination, and we exploit that we can do early termination. So the algorithm for this is really simple. We just sequentially interleave the steps of pre-star and post-star. So I included this algorithm because there's not really much to it. So we initialize both pre-star and post-star, and each of these algorithms internally use some work set of transitions that we have left to process. Then we do a step of pre-star, and we do a step of post-star, and so on. And in each of these steps, we add transitions to the product and check if there is a non-empty intersection. So I'll show in a bit the experiments where this actually makes a huge difference. Intuitively, for me at least, bidirectional search, when I think about it, is in an undirected graph, and that doesn't seem like it's going to be that big of an improvement. But the difference here is that for push down, the search space is directed. So there can be a huge difference between the size of the forward search space of C and the backward search space of C prime. And I think that's the intuition to why this can help a lot. Finally, we use this technique called CGAR, so counter-example guided abstraction refinement, and it helps us reduce the size of the pushdown that we analyze reachability on. And of course, if the pushdown is smaller, then reachability analysis is faster. So the way we do abstraction is that we group together links in the network, and we also group together labels, and then we do an over approximation abstraction so that if any of the individual links or labels in a group would cause a rule to be in the pushdown, then there's also a rule between these abstract states. So when we do an over approximation, it means that if there is a trace in the network, there will be a trace in the pushdown. So when we have a negative answer from the pushdown, we already know there's no network trace. Otherwise, we have a trace and we try to reconstruct the trace in the network. And if this succeeds, we are happy. Otherwise, we need to refine the abstraction. And often for implementing CGAR in a concrete system, the challenge is how to find a refinement based on the failed reconstruction of this counterexample. And in the paper, we show how to efficiently do this based on this spurious counterexample. Now, if we need to refine the abstraction too many times, it doesn't really help on performance because the reachability analysis is relatively fast, and we need to go through the network data structure every time we refine. So to set us off on a good starting point, we use some heuristics to make an initial abstraction that's close enough to what will eventually give us the answer. So for the performance evaluation, we pick some real network topologies from this database called Internet Topology Zoo. We pick the 10 largest because we want to show scalability. And then we have implemented a tool for generating these forwarding tables using some industry standard protocols. So we get some data planes that are realistic to what you would find out in the wild. We use some different settings to get 40 data planes. For each of this, we generate queries randomly based on some templates. And these are properties like reachability, waypointing, loop freedom, service chaining, transparency. And we use various levels of number of failures. In total, this gives us a benchmark set of 60,800 queries. And we have adjusted these templates so that there's a roughly even distribution between positive and negative queries. We run each of the tools and we sort for each tool, we sort the computation time and show them in this plot. So we compare to two previous tools, Moped, which was the original tool that did push-down reachability, and then Allwines, which is our prior work that did not have these techniques. I hope you can see the labels on this plot. So first, the difference between these two lines called Allwines and these two lines called pre-star and post-star. It shows the improvement done by our early termination technique together with an improved translation from network problem to push-down problem that we were able to do because we had this early termination technique. Next, this difference between the pre-star and post-star lines and this black dual line shows the improvement of the bidirectional search. And note that our y-axis is logarithmic. So this is an improvement of, say, 5 times or 7 times or something like that. Finally, the green line. So Segar turned out to be faster in 27% of the cases, but in other cases it was a lot slower due to having to repeat this refinement too many times. So we proposed to run Segar in parallel with dual and then take the fastest, and this gives us another bit of improvement here. So all in all, this is about an order of magnitude improvement to the prior state of the art. In summary, we have presented 3 techniques for doing faster push-down system reachability analysis: the early termination based on some on-the-fly computations, bidirectional search combining 2 classic algorithms, and counterexample guided abstraction refinement. We get an order of magnitude speed up, and we believe this will help make network and verification of MPLS networks usable in practice. And finally, we have published all our experimental artifacts, and we have put our source code on GitHub. Thank you very much.
Thanks, Morten. And this work looks really impressive. It's really impressive in terms of performance improvement and the system design. Is there any questions from the audience for Morten for his presentation? Okay, if there's no questions, I may have one question and one comments, or maybe one comment or questions for you. my first question that you in your experience you showing that sometimes the cigar can improve the performance by 27%. And sometimes you say sometimes the cigar does not improve the performance due to the expensive abstraction and refinement. All right. So
just to clarify, so it's in 70% of 27% of the cases we improve performance, but it's up sometimes up to an order of magnitude.
Yeah, I understand.
Yeah.
I understand.
Okay. Yeah.
So my question is that if we want to use a system, do you have any suggestions when to use cigar or when we should not use cigar for, let's say, cognitive performance?
So in cigar in general, or for this this system?
Yeah, under what scenario cigar will be used for, and under what scenarios we should not use cigar. But after all,
so yeah,
cigar
so
is
if there's a lot of
right. Mm-hmm.
Yeah, so cigar helps if you can say there's a lot of redundancy. So in terms of for example, labels or states that have the same behavior and hence would give the same answer if you group them together. So
Okay.
I think the reason why cigar doesn't perform as well here as you might have seen in other applications of cigar in model taking, I think it's because we have a polynomial time algorithm and we have these other optimizations that actually make it quite fast in the first place. So the bottleneck here is actually going through the data structure of the network. So it's not the cigar process itself, it's just the time it takes when you do these repetitions. It would be nice if we knew like exactly when
not to use it. Like,
sorry?
Well, is there any possibility we have a pre-check about the product? So we will find that sometimes there's a lot of redundancies. Maybe cigar is a good choice, but otherwise we just not using cigar for refinement abstraction, which can further allow us to improve the performance.
I'm not sure I got the question.
So can you hear me?
Yeah, I can hear you.
Yeah, okay. So my question is that is there a runtime detection system to evaluate the problem for the initial stage so that we know that a cigar should or should not be used for this problem?
Yeah, I think it's a good point. Like, how could we like magically in a smart way know when a certain method or algorithm is good to use?
Okay,
yeah,
my last question is that your technique seems very general to me, not necessary for the network routing system. So what do you think? What other kind of system can you apply?
So other types of problems that would
can be generalized
that you could use for pushdown systems.
Yes, for pushdown systems, and also can apply your faster verification. Yeah,
so I think these algorithms are quite specific to pushdown systems. Of course, we frame them in a more general light. So I know pushdown systems previously have been used to verify things about
I'm not
data
specific to the. I'm not saying the pushdown system. I'm saying what I'm talking about the network routing system. So apart from a network routing system, what the other system can approach be generalized and applied? It's okay. I just have a minor question. If you don't have the answer.
Yeah, I think also some of your words I don't really quite get.
Okay, my question, maybe I can repeat again. My question is that apart from the network routing system, which you apply you convert it into the pushdown system, and do the verification, and what other scenarios or what other applications can you also convert the problem into a pushdown system?
So this so as I tried to say, prior work, so this work by Stefan Swan and others in the early 2000s did data flow analysis of programs. So they used the pushdown system to model the essentially the call stack of a program where they call between procedures and make some analyze some properties of these programs. So this is the thing I know about. Of course, other models would also, I don't know. It would be nice if we could
Okay.
find more problems to analyze using push-down systems.
Okay. Okay. Let's thanks Morten again. Thanks for this impressive presentation. Now let's move to our last presentation, and it is about live analysis. So the presenter will be Nicholas. Let's welcome Nicholas to give us the presentation.
Yes, hi. Let me just share my screen. Okay, can you see my slides?
Yes, we do.
Cool, thank you. Okay, hi, I'm Niklas. I will present to you our paper Live Synthesis. And this is joint work with Ben Finkbeiner and Felix Klein. I want to kick off my talk with this small and short video. What you see here, I hope you can see it through Zoom, is a car park with a lot of cars that are actually blinking each by their own. And what happens here is all these cars get a firmware update. They get a new software deployed over the air without any mechanic actually operating on it. And this is very interesting because these systems are actually running. And of course, some modern systems are always on, so they never get shut down. But of course, all these systems also need maintenance. Another potential example would be a power plant that could also never be shut off. But of course, you need to increase the security also of these systems. And the main observation that I want to stress out here is these always-on systems outlive their initial specification. Once they get deployed, of course, they are specified and implemented in the way the specification tells them to. But during their lifespan, they get new specifications and then, of course, new implementations because they have to be correct. And well, in our scenario, if you want to synthesize such systems that then get deployed as updates, we need to be aware of the past of these systems. So we cannot ignore, as we normally would do, the past of a system, then synthesize a completely new implementation, plug it into the system, and then keep going. This could lead to drastic errors. Well, this is a very concrete example. Let me move to reactive systems here. In reactive systems, we essentially also consider always-on systems. Once you start them, you have inputs and output chains, and you let them keep going forever. So you only look at infinite executions. In our example, we have this black robot here, and this black robot is implemented in a way that he satisfies the specification, reply to request with measurements. So assume he's on maybe Mars, or choose your planet, and it interacts with Earth and gets his commands from Earth as inputs, then performs some actions and outputs again. And of course, if Earth wants a new measurement, it requests one and the robot answers. But maybe after deploying the robot, he landed on Mars. Let's say we need to perform an update because either some environmental change that we could not know by deploying the robot happened, or we actually need to refine the specification on some other course. And in our scenario here for this example, we say, well, please avoid spurious measurements. So whenever there's no request, please also do not measure, maybe because of some power limits. And what we would do here, we would synthesize a new robot, the blue robot here, plug it into the whole system, and just keep on running and let him output and receive the inputs and provide us with the outputs. So what actually happens here is if we allow live updates in reactive systems, then we do not only have one explicit implementation that is then run forever, but we get a sequence of implementations. So we have one black robot with one phi0 specification, it will be executed. At some point, this execution has to be interrupted. We have a new blue robot satisfying a new specification, and so on. And there are some interesting questions that I try to answer in this talk, or to try to give solutions in this talk. The first one is, when is such a live update actually correct? So of course, you could just plug in, forget all your past. This is what we will do right now. But maybe there are some problems there. And indeed there are. How can we specify correctness of live updates? So what is a good way to specify them? And of course, in the end, how can we synthesize correct live updates? If we only look at the functionality of replacing the old implementation with the new implementation, there's actually lots of research in many research areas. I only want to stress out two papers here. One is about dynamic updating Java applications. So it is essentially possible during runtime of your application to change the implementation of some modules. So in this case, if you have new implementations for your interface, you need to update them. You can just plug it in during execution. So programming language is one very interesting field. The other one is operating systems. And I just picked one here, which is very user-friendly, I would say. Here you can adapt your Android kernel during runtime. So on your smartphone, if there has to be a, let's say, a security patch, and the user wouldn't even notice that this patch is deployed. Okay, so actually just changing your implementation is possible. And we're now looking at how can we ensure that the behavior is still correct after changing your implementation. Okay, in the world of reactive systems, we're looking at linear time temporal logic, LTL. And if we have a LTL specification phi, yes, that works, then this phi defines a language, and this language collects all traces that satisfy, with this semantic operator here, satisfy this specification. For our black robot, we can build this LTL formula, well, for both measurements that you can do. So we have 1 and 2, if there is a request. So whenever there is a request, eventually, so after some finite time, reply with some measurement. And well, for the blue robot, nothing much changes. He still has to reply with measurements, but out of simplicity, I just wrote it down here. You do not, you also have to guarantee that there are no spurious measurement. You do not waste your energy, so to say. If we look at our implementations for these systems, well, then we consider transition systems. So we have states labeled with the output from the robot, and edges labeled with the inputs of the environment. The implementation is very easy for the black robot. Maybe to note here, of course, we have mutual exclusion. You cannot perform 2 measurements at once. So whatever input is received, we switch between the states. So every 2 steps, you do actually perform the measurement for every request, even if there is one. If we look at the blue system, which is actually reacting to the environment inputs, it does branch according to the inputs. Let's say if there is no request, then actually do not output anything. But it also stores the information which request comes. So if there only is a request for measurement 1, then also only output M1 by switching to the state. Okay, so these are the 2 transition systems that we actually want to update from the one to the other. And now we want to synthesize the update transition system, which is the blue transition system. And synthesis is, well, given such a formula that now describes the blue robot, and we have to find a transition system such that all traces are entailed in the words, so in the language of our formula. If this is the case, well, then we get a correct transition system by default. If this is not the case, then we actually cannot find an implementation for this formula, and we call the formula unrealizable. So essentially, we have one synthesis procedure which gets as input the formula and outputs our transition system, here denoted as our blue robot. Okay, now this gets a bit more complex if we actually add an evaluation for live updates, and we change LTL to this functionality, and we call it live LTL. So actually, you do not have only one specification, you do have two specifications, and you also have a finite execution between these specifications. And there are some interesting design decisions to be made here. And all are based on the question, what is the impact of the black robot to the new update? If you say, well, we just take the previous specification and also enforce it on the update system, well, then it also would have to be a refinement of the update specification, and you could not be free of choice for your update. And this is infeasible, for example, if you have some safety guarantees that actually need to be changed, then you would never be able to verify your update. And if we look at our formula, well, there is cases where there are requests, but they are not answered yet. So we only have to answer them in some finite time. And this is something that is natural to allow, and that is natural to actually bring to the update robot. So what we consider as possible, as we call them, obligations for the update system is, well, it could be that you have to satisfy eventually measurement 1 or 2. It could also be that both requests are not yet answered, or it could be that every request that you had up to now is actually answered by the robot, and the update system can just disregard the previous execution. So the statements that we're doing here and the decision that we take are, well, these obligations cannot be stated after termination. So whenever the black robot is terminated, it cannot open, so to say, new obligations to the update system because it is essentially terminated. And the second thing is, these obligations need to be satisfiable in finite time. This is where we exclude liveness and safety, and we only look at co-safety properties that will then be transferred to the update system. And based on these decisions, we actually define our live LTL logic. And now, compared to LTL, we have two specifications. We have one finite execution, and we build the words over these three parameters. So actually all three of them are important. And now we have two semantic evaluations, the one here and the one there. And to give you a picture here, what we actually do is we connect this finite execution here to all the traces that can happen after that. So we actually have a set of traces here. We evaluate the transition from the previous execution to the update system with the first operator. And for the second specification, well, the second semantic evaluation only considers everything that happens here. So we actually split this in two parts because at the point where the update happens, we need to change the behavior of the initial specification, and we need to change the verification exactly at this point. So this is very interesting what happens here. Just to summarize this, the first semantic evaluation transfers the obligations and limits the impact. So these are the two statements that we made. And the update semantic evaluator shifts the evaluation to the update point. So it takes the LTL formula, shifts it to exactly the correct position, and then evaluates as a normal LTL. I have some examples here. I don't have the full semantics. I would refer to the paper for that. But it's very interesting what happens here. So if you have the infinite trace of the previous transition system, which satisfies next B. Now it really depends where you crop off this trace, where you initiate your update. If you do it before satisfying next B, then the transition system actually has to satisfy B. It will be transferred. If you crop it after this specification was satisfied, then you actually don't have to satisfy anything for the update. This is a finite time formula. So maybe we can go to a co-safety formula. If we have A until B, and we're on our infinite trace that actually satisfies A until B in the fourth step, if we crop it the step before, then we actually take the whole formula and bring it to the update position. This is still an obligation. The B still has to come, and until this B comes, A has to hold. So this is also something that we bring to the update system. As a negative example, consider globally A. What happens here is this is a safety property. For every step, so the globally defines for every step, there has to hold A. And this is something that changes the infinite behavior of the update system. And this is something that we actually kick out by updating. So it does not depend on where we actually crop this trace, but the globally A will not be transferred to the update. But globally finally A, what happens here is, this is actually the example from a robot. In every step, the finally A is stated. So this is the semantics of the globally. And we satisfy it here, but in this step, it is again opened. So there is again finally A to be satisfied. And this finally A is the only thing that we transfer to the update, because this obligation actually was not yet satisfied. If it is satisfied in the last step, we can verify this with standard LTL semantics, then we do not transfer it to the update. Okay, now we have a logic that actually tells us when a trace is correct according to update. Now we can define our live update problems. And we have two versions of our live update problem. The first one is called finite trace live update. So this is our white box approach. And by white box, I mean that we actually know the explicit execution of the previous system. So it can be a very long execution, but we have it at our hand. And we only have to verify it against this explicit execution of the previous system. We know exactly what happened, and we can essentially remember what we have to satisfy. So it is formulated as follows. The finite trace live update is correct. Well, if for all traces of our update system, if I connected with the previous execution, then it has to be part of the live LTL semantic. So we take a logic, connect all these traces, and then we can check if the update transition system is correct. So as you see here, we have this whole trace. We connect it to the transition system. With that, we can form all the traces that we actually enumerate up here, and we can check if the update is correct. And this trace eta 0 here might be very large because we do not know when our update is performed. It can be performed after an arbitrary number of steps. And this is why we also introduced a black box version. It's called the universal live update. And the name comes from the fact that, well, now we do not know the finite execution. We only know the previous transition system. So we know the implementation of our black robot, and we, of course, know the specification. And now we have to ensure that our update system is correct for all possible finite executions of the previous implementation. So we have to consider all possible obligations, so to say, that can be stated for us. If we again look at the definition and the picture for it, now we lose in our precondition the eta 0, and we have a universal quantification over all finite traces of the previous transition system. And how this looks like, if we just visualize it, well, from every state, I could potentially take the update edge. So we could perform an update from every state and in every time. So it's actually not in our, we cannot decide when this update actually happens. Okay, we have our update problems, and we now want to synthesize correct update implementations for these problems. So we actually perform live synthesis. And the live synthesis problems now also follow these structures. If you remember the picture before, we only had the formula for synthesis. Well, now there's a second parameter. We also have a previous system. We know that the previous system actually satisfies the previous specification, so we do not have to check this. This is something we can assume. And for the finite trace update, we also know the explicit finite trace, and we search or we synthesize a transition system such that we comply again to our live LTL semantics, only appended to that explicit eta. Interestingly, also, if you find a solution, then we also know that it is correct for this trace. If not, we can actually not find a transition system for this explicit update context or for this explicit trace. For the universal update, it looks much the same, but we do not know the trace here. So we also have the quantification over all traces. So we actually have multiple possibilities for our initial system. And then we have to find one transition system that complies to all these previous executions. Okay, our methodology for that, how can we actually compute these obligations, is the obligation monitor. So what happens here is, well, to know if this, to know what we actually have to synthesize, we need to know the formula that is still to be satisfied by the update system. And it is determined by two things, by the previous specification, but also combined with the implementation, because both of these things are interdependent, and we need to build a monitor, or we do build a monitor that tracks the states of the implementation, but also the possible formula evaluations. So as you saw before in the examples, we actually unroll the executions on the semantic evaluations of LTL. And what we get then is, well, for all these inputs that I can feed into the obligation monitor step by step, we actually can, based on the labeling of this monitor, obtain the exact obligation that I need for my update. And this is very helpful for both update methods. For the finite trace update, it is sufficient to only look at the current formula that I now extracted. So I have my my trace at hand, I can feed it in the obligation monitor, and I obtain that explicit formula as an LTL formula. And for the universal update, actually, the state space here defines all possible obligations that I can reach. So I can use this to obtain all state labels and then synthesize a solution for that. If we look at the complexity results then, so this is our methodology, and this is now the complexity. We stay in the same complexity bounds as for LTL, and we use as our parameters, of course, both specifications, because either specification could essentially blow up this process. We also did this for model checking as a side note, so that the problems are structured the same as for synthesis, but translated to model checking. And we actually also stay in the same LTL bounds here. What happens for model checking? Well, we can combine the transition system and just encode the update in the formula. What happens for the synthesis part? Well, now we have a previous execution and we do not know when this update actually happens. So we have to give this choice to the environment. If we do this, then the jump to the new formula can actually be at an arbitrary point in time. And we synthesize a strategy that actually, independent of this choice, is correct. Okay, we implemented all of this. So we implemented the obligation monitor for specification and an implementation, and then synthesized solutions for our update problems. We used the benchmarks for robot specification patterns and from the synthesis competition. And of course, all these benchmark specifications that we updated from and to raised obligations for the update. And the most interesting thing here is it really differs from specification to specification. So I only picked 3 examples here. If you consider a full arbiter, which is no spurious grants can be given, then you actually cannot satisfy realize a universal update. But there are some finite traces that you actually can perform a finite trace update from. And this is because, well, if you have a grant that is unanswered in the update system, there are always executions where you could never answer this grant without being spurious. If you have a simple arbiter, then actually nothing bad happens. You can just, as the update system, satisfy all grants that are open, and you actually be realizable. Okay, all these implementations and results can be found in GitHub. Okay, let me summarize my talk. I introduced to you the notion of live updates in reactive systems, where we actually now have a sequence of implementations during your execution. I introduced the live LTL, which actually gives us a logic to reason about the correctness of live updates. I showed you our synthesis approach to actually construct correct systems. And I showed you our experiments, which show that it's actually needed if we update from some specification to another during runtime. Thank you very much.
Okay, thanks, Nicholas, for this very great talk. It seems very solid to me. From the audience, is there any questions for Nicholas?
I have a question, if I may.
Sure.
So, well, thank you very much for your talk. I was wondering, for the universal case, is it the case that you might have 2 finite traces that require 2 proof obligations that are incompatible? So meaning one finite trace requires the new system to satisfy phi, and the other one would require it to satisfy not phi. So basically, this makes it unrealizable.
Yes, this could happen. Well, normally this is the case if you have some environment assumptions. So if this behavior is possible, so at some point you have to satisfy something that would be violated in another trace, then you have to be able to differentiate these traces and do not answer with the same reply to some environment. So if this is the case, then we actually, based on the previous specification, cannot perform an update. We have to know in which situation we are. So then we need the finite trace live update, yes.
Okay, so as a follow-up to make sure I understood correctly, the new system doesn't have any kind of visibility on the past, meaning on the finite trace of the old system. So
in the universal, yeah.
When you replace the system in the universal case, the new state machine, let's say, doesn't know anything about the steps taken by the other machine.
Well, so it knows everything, so it knows the previous system, but it does not know the execution. So it actually has to assume that any execution is possible up to that point. Yeah.
Okay, because I was wondering also for my previous question, if you had some kind of history variable or some way in which you can expect what happened before, then you could distinguish the 2 cases and say, I'm in this situation, so I have to satisfy this property, or I'm in the other one.
Yeah, in the same direction, you could also say, I know that I have n time steps up to now, and this also limits the obligations that you could reach. So there is stuff that you could do there, where you not give full information of the explicit part, but only partial information on the previous execution, which would essentially help, yes.
Thanks.
Thank you.
Okay. That's also seems a very good questions. Is there any questions for Nicholas?
I have a short question. Have you compared your LTL logic with some of those different variants of LTL used in runtime verification? See, some of those variants in runtime verification LTL is also, some of them are also for finite traces.
Sorry, to what in runtime verification? Didn't get that.
Those different variants of LTL logics for runtime verification. Some of them may be very similar to the live LTL, I think. I was just wondering, have you considered those ones and have you compared them?
Yeah, so I only can think of the 3-valued LTL version for runtime verification, where you essentially do not know some value. So I agree with you. There are some similarities with runtime verification. Essentially, when we track these obligations, then it is actually we're actually tracking the execution and monitoring the execution. But the logic, I think, is incomparable. But I had to look at I would have to look at this again. Yeah, thank you.
Yeah, I think I've seen one of them, which is called finite trace LTL with what's it called, with a week next. And it sounds very, I think it shows some similarities with this. And maybe your work can also be extended with a similar tool for runtime verification as well.
Okay, I get your point. So the similarity is, well, we have this finite execution, but what then happens in this in the logic you mentioned is, well, we evaluate in the last step differently. We also do this, but we do not decide in this last step if we are correct or not, but we actually extract something out of the formula. And this is really extracting, we're taking the formula that we reached at this point semantically, and then have some performance on them. So yeah, there is similarities because we have some finite trace, but we do not use it as finite trace because we actually want to transfer everything that is left open to the update system.
Definitely, yeah, it's a very good answer. Thank you very much.
Thank you.
Okay, in this case, let's thank the speakers and the audience again. Thank you for your attendance. And Joe, do you want to announce anything for the next the keynotes in next half an hour?
I don't have any announcements right now.
Okay.
So I guess this is the end of this session. And in half an hour, we'll have the second keynote. And Professor Jin Song Dong would be the chair. And Andrea would be our keynote speaker. So yeah, really looking forward to that. So see you guys in half an hour.
Okay, and thanks everyone. Then let's have a rest and looking forward for the keynote. Bye.